Hi, Les Struven with a video on equipment selection based on the results of your heat loss and heat gain calculation. In this example, we have a heat loss of 68,332 BTUs and a heat gain of 28,974 BTUs. The first thing we need to do is select a furnace that has an output of greater than 68,332 BTUs. So if we look at the available furnaces, we can see that the 80,000 BTU furnace has an output of 78,000 BTUs, and so that will satisfy our calculated heat loss. Now you'll notice that there are two 80,000 models to choose from. I always suggest you start with the first one and see if that works out. Now also take notice of the certified temperature rise, because this is an important factor in your overall consideration. Nextly, we need to establish our condenser and evaporator size. So when you take here essentially 29,000 BTUs and you divide that by 12,000 BTUs per ton, you get very close to 2.5 tons of cooling. So in this example, we would select a 2.5 ton condenser, and it may be possible to choose a 2.5 ton evaporator, but I think there's a good chance we have to go to a 3 ton evaporator because of the airflow requirements. So now that we've got this information, you can go to the static pressure determination worksheet, and we can put in some of our basic data. We've got our heat loss, heat gain, we've got our furnace output, our condenser output, we've recorded our temperature rise minimum and maximum. When you run through the optimum temperature rise CFM equation, and remember the equation is the furnace output divided by 1.08, which is a constant, times the maximum temperature rise minus 10 degrees. So in this case, the maximum temperature rise is 70 degrees, so 70 minus 10 would leave us 60 degrees. So when you substitute the numbers in here, we get an optimum airflow rate of 1,204 CFM. Based on our optimum cooling CFM, we've got our cooling output times 400 CFM per ton. So you've got 2.5 tons times 400 CFM gives us 1,000 CFM as the airflow rate for cooling. So in this scenario, it's shaping up that the heating CFM is quite a bit larger than the cooling CFM. So it's in all likelihood our heating CFM will become the design CFM. So at 0.5, we need to go to our blower chart and look for airflow rates that are as close to 1204 as possible. So when we look at the available airflow rates for our first 80,000 furnace, we can see that in the 0.5 column, we have an airflow rate of 1240. At 0.6 we've got 1200, and at 0.7 we've got 1165. Now we could possibly look at the the next size furnace, this 80,000. Now the second 80,000 furnace has got some good heating airflow rates, but it doesn't have any decent cooling airflow rates. If you recall, we need 1,000 CFM for the optimum cooling, and with our first 80,000 furnace, we've got some values here at 1,015, 975, and 935. But in the larger 80,000 furnace, we've got nothing close, really, other than in this lower end. And so I would suggest that we stick with the smaller 80,000 furnace in this scenario. So our three heating speeds are going to be 1240, 1200, and 1165. And our cooling speeds are going to be 1115, 975, and 935. And so that's what I've got here. Once you've selected those airflow rates, you want to make sure that the heating airflow rate gives you an adequate temperature rise. And so we've got very good temperature rise coming out with these airflow rates, so we know that the furnace will function properly within this range. So now the next thing we need to do is look at our coil. Now we can see that our heating airflow rate is quite a bit bigger than the cooling airflow rate, so we'll have to establish what coil size we're going to use based on the heating airflow rate. So our heating airflow rates are up at 1240, so that means we need to have a coil that can handle in excess of 1200 CFM. So when we have a look at the coils, you'll notice that the 2.5 ton coils can handle only a maximum of 1200 CFM. And so these coils could be too small. So that leads us then to the next size up, which is a 3 ton coil. And so we can see that the 3 ton coil can handle up to 1400 CFM. So we can go through the first scenario with the physically smaller 3 ton coil, so that'll be the 36L17. So when you substitute the airflow rates and the coil pressure drops at 0.5, we end up with an available static pressure of 0.125. So as you know, the range is between 0.25 and 0.35, so this available static pressure is way too low. Now if we substitute into 0.6, again you've got your airflow rates, your cooling, coil pressure drops. We end up with an available static pressure of 0.24. It's getting better, but it is still lower than our minimum of 0.25. So now if we go to 0.7, once again substituting in our pressure drops, we end up with an available static pressure of 0.35. Now theoretically, this is still within that range of 0.25 to 0.35, but it's right at the top end. And it is slightly exceeding that maximum of 0.35. So I would suggest that this particular coil, the 3 ton L17, is in fact on the small side, and we don't want to use that coil. So then the next thing is to substitute back in, but using the next coil up. So once again, you're going to input your airflow rates, but with the associated pressure drop. At 0.5, we come up with 0.21. So that's better, but it is still below the 0.25 minimum. So let's have a look at 0.6. So substituting the coil pressure drops, we have an available static pressure now of 0.323. And clearly this is nicely within the 0.25 to 0.35 range, so it appears that 0.6 could be our design static pressure. And just to verify, we substitute in at 0.7, and we find that our available static pressure is 0.43, and therefore this 0.7 is too high, and so that's not a good external static pressure to use. So based on the equipment available, we're going to use a 36L21N coil, and the furnace will operate at 0.6 inches of water column static pressure. So that brings us back to our equipment selection, and so we've got a keep right with our G9 MXT 080 1716 furnace, output 78,000, our temperature rise 40 to 70 degrees, and so as we found out, our external static pressure is 0.6, and at 0.6 we've got a heating airflow rate of 1200 CFM. Our cooling coil is the 36L21N coil. Our condenser is 30,000 BTUs, so that's 2.5 ton. Manufacturer's airflow rate is 400 CFM per ton, so that our target airflow rate for cooling is going to be 1,000. But the actual airflow rate based on 0.6 is 975. Our coil pressure drop, because is going to be 0.177, and that's based on a dry coil, because the heating airflow rate is larger than the cooling airflow rate, and so the coil is going to be assessed at a dry condition. If the cooling airflow rate is equal to or greater than the heating airflow rate, then the coil pressure drop would be assessed on a wet coil. Our speed settings happen to be the blue lead from the motor going to your heating spade connector on the circuit board, and on the cooling side you would have the orange lead from the motor going to the cooling spade connector on the circuit board. The circulation airflow rate, which is based on the overall volume of the house, in this case 26,000 cubic feet, times a rate of 0.025 gives us an air circulation rate of 652 CFM. So based on these three different airflow rates, you have to select the largest airflow rate as your system design. So clearly 1200 CFM is the greater of the three, and so that becomes your system airflow rate. To get your cooling airflow proportioning factor, you will take your cooling airspeed, which is 975, and you will divide it by the cooling subtotal of 27,516, and that'll give you a proportioning factor of 0.0354. And you do want to carry 3 to 4 decimal places in your proportioning factors. For the heating proportioning factor, you're going to take 1200 CFM divided by the subtotal heat loss of 66,534, and that will give you a heating proportion factor of 0.018. Then to verify, you've got a calculated temperature rise of 60 degrees, which is very nicely situated within the range of 40 to 70. Our filter pressure drop is 0.1, determined from your equipment selection spreadsheet. The coil pressure drop, again coming from your external static pressure spreadsheet, so that the total coil and filter pressure drop is 0.377, so that 0.6 minus 0.277 leaves us with an available static pressure of 0.3 0.323. And once again, this is nicely within the range of 0.25 to 0.35, and so this will become the available static pressure for determining our duct sizes.